gonna try to aim roughly 40 minutes, and then feel free to stop me if it's getting too abstract. And I don't know what the hell I'm saying. Generation zero intervals, intro, fifth year PhD student. I started working out on dynamics of childhood diseases in the beginning of PhD, and then when that was 2019 and 2020, COVID hit, and so we all know what happened after that. Everyone started working on COVID, and so did I. And then one of the things that got me interested is this problem of understanding generation intervals. So today I'm going to be talking about giving some intro and on generation interval, and then working through some of the theories that I've been thinking about in terms of generation interval, and how does that, thinking about serial intervals, which we can sort of measure in practice. Sorry, Sam typed something in chat and distracted me, and then talk about some applications of my work. I'm hoping the first one will be familiar to most people. Second one, some people. Third one is sort of the new stuff that I haven't presented before or published yet. Then it's a little abstract. So I hope I can get through. And the fourth and fifth is hopefully more tangible and useful. So what's a generation interval? It's very simple concept. It's a time between when someone gets infected and then when they infect somebody. For example, here the pink person's infected on day 3, and then they go out and they infect this white person on day 8, and then we have a generation interval of 5 days. So you go around infecting people, and so it provides a time scale of how long it takes to infect someone else. And why do we care about generation interval? Because it tells something about, it allows us to link growth rate to R naught, the basic reproduction number. So for example, here we have 2 epidemic processes which are at the doubling at the same rate at the population level. So if we're looking at population time series, you probably can't tell the differences between the two. But on the left-hand side, we have a much long generation interval that's double the epidemic on the right side. And that this means that since it takes longer time to infect someone, your R naught has to be much larger to make an epidemic that grows at the same rate. So given epidemic growth rate, a generation interval, longer generation interval typically leads to higher R naught. This is the basic theory, and this is why we kind of care about try to get accurate estimates of generation interval, especially during early outbreak. So one of the work I did is looking in the beginning of COVID outbreak. There was large variation in R naught estimates for outbreak in China, even though everyone was essentially looking at the same epidemic. So everyone was observing same growth rates, but they were all estimating different R naughts, ranging from something like 1 point something to 6 point something. And so we argued in the beginning of outbreak that these variation in R naughts were likely driven by their assumptions in generation intervals. And we showed that you can try to break down their estimates in terms of growth rate, the mean generation interval, and then what we call generation interval dispersion, which is just a coefficient of I think it's a coefficient of variation. I can't remember if it's squared or not, but I think it's a coefficient of variation. But yeah, so you can break these apart and then try to compare these what seems like disparate estimates of R naught into disparate estimates of generation interval. And likewise, generation intervals are also very important for estimating RT estimates. I think many people on the call are fairly used to this kind of figure, try to get RT estimates for time varying R naught estimates for COVID-19. And okay, sorry, I have to check what slides. I can't do this. Oh, I have the slide here actually. So yeah. So I'm gonna talk about, so soon I'm gonna talk a little bit, actually I'm gonna go deeper into how do we actually define RT. And so to do that, so how do we think about, did I freeze? Oh, okay, I'm back. How do we think about generation intervals? How do we come up with a theoretical framework for understanding generation intervals? The way I like to do it is, some people like to do it in terms of probabilistic framework, but for me, it's a little confusing. I find it a little confusing because it's hard to put probabilistic framework into a dynamic model. And instead, it's for me, I find it most useful to think about what I call kernels. So we have a k of tau, which is the rate at which secondary infections are generated by an average infected individual. And we can decompose this into two factors. The integral of k of tau is R naught, the reproduction number or the base reproduction number. It tells us how infectious, it tells us something about the total infectiousness of an infected individual. And then normalizing the total kernel by R naught tells us generation interval distribution, which tells us about how long it takes for someone to essentially infect someone. It tells us about the individual timescale of individual level transmission. And then the nice thing is that the kernel, we can generalize the kernel and write kt of tau, the average rate at which secondary infections are generated at time t by the individuals infected tau units ago. And then we can further write I sub t minus tau at t, which is so product of it of tau, which is the number of people who are infected tau at time t of tau, and then kt of tau is going to tell us about how many they're going to infect at time t. So t sub tau of tau, t of t. Sorry, that's is the density of new infections at time t caused by individual who are infected at time t minus tau, and then integrating over the subscript, which is a time of infection. So a subscript is representing when they were infected, and then time t. Yeah, it's not very clear. Sorry, tau so subscript is when the infectors were infected, and then the time in bracket t is the time of current time. So integrating over the time of infector, we get this renewal equation. And then if we assume, which most people do, is that k of t of tau is can be decomposed into a RT. So the infectiousness component, the g of tau, the generation interval, then we get this famous renewal equation, which is used for estimating things like RT. And so for the next several slides of my talk, I'm going to be breaking down these. I'm going to be utilizing this framework and then breaking down and explaining a little bit more about when does this assumption make sense, what does this tell us about generation interval, and things like that. So actually, I'm going to pause for 1 minute and ask whether any questions. Should I be slower or fine? If I don't hear from anyone, I'm going to assume
maybe like a little less math, if possible.
Yeah, sorry. I can try to explain a little more biology, but I do have some more math on the slides. So
all right, just do your thing.
Yeah. Okay, so we're gonna use kernel to understand renewal equations. So to move on to intrinsic and generation intervals. So far I've introduced that you can try to express generation interval. So I think there's this generation interval distribution, but we can try to distinguish them a little bit more carefully. And then it turns out we can think about different types of generation interval distribution. First, there's intrinsic generation interval distribution, or what people like to call intrinsic generation interval distribution, which measures intrinsic infectiousness of infected individual. Some people have called it in the literature as infectiousness profile. So, and it's a very vague concept. I'm gonna demonstrate later why it's vague, but it's essentially what gets used in these kinds of renewal equation framework. It's what's used for estimating RT, and people sort of take it as granted that there's this hypothetical distribution you can come up with that measures intrinsic infectiousness of infected individual. It's magical distribution that we can use for calculating the incidence or estimating RT. It's vague. It's supposed to be vague. But instead, something a little bit more concrete is the realized generation interval, which measures the actual timing between transmission events. So for example, let's imagine we have an outbreak that looks like this, very typical trajectory and outbreak that goes up and down. Then imagine we take everyone who was infected at day 50 and then measure when they transmitted their infections to other people. So this is now we're looking at actual transmission events. In particular, we're starting from the infectors who are infected on day 50 and going forward in time, and then asking when they infected someone else. And we call this the forward generation interval distribution. And then this allows us now to quantify how generation intervals are changing across time. So we from a reference of because we can take a group of individuals who are infected at different time points, and then look forward in time. And in this particular, for a very typical outbreak trajectory like this, we usually see that the forward generation interval decreases or contracts over time. And then the reason is, in this case, susceptible depletion. As a susceptible pool is going down, meaning when susceptible depletion is happening, that means you're less likely to infect in the future. Because, so let's say I'm infected right now and the susceptible pool is going down. That means I'm going to be less likely to encounter a susceptible individual in future than later than earlier on. So that's going to cause decrease in the generation interval distribution. And then to make this a little bit more concrete, let's imagine
Daniel.
Yeah.
Sorry, could you just define forward, please? I think we might have missed that.
Yeah, forward as in we're looking ahead in time. So again, we're looking at people who are infected on day 50, infectors, and then ask when they infected another person. So we're looking forward in time rather than looking. So if we were to look at backward, we would take people who are infected day 50 and then ask who they got infected by. Instead of looking at infectees, we're looking infectors, we're looking at infectees, we're looking at future events. Make sense? I think.
Yeah, thank you.
Yeah. No problem. And then now let's try to be a little bit more concrete. So here, the gray line is showing a kernel, is showing when you would infect without intervention. So A is showing what would happen if intervention kicked in. So black line is sort of representing some kind of intervention. So what would happen if intervention kicked in on day 5? Since day 5, so you're infected at day 0, and the intervention kicks at day 5 and reduces your transmission, which is represented by a red curve. And then now, so you're less likely to transmit after day 5. That means that's going to decrease your generation interval because you're no longer transmitting. This gray area is no longer transmitting. On the other hand, if you're infected during an intervention period, let's say, so now we're in a lockdown and then you were infected, then that's going to reduce the overall infectivity, your transmissibility throughout the course of infection, but it's not going to affect your generation interval because your infection is decreased equally throughout your course of infection. Instead, imagine imagine that intervention was lifted during your infection on day 5. So initially you're wearing a mask, and then the government tells you, oh, you can stop wearing a mask. And day 5, you throw out your mask, and then you're going to now start going around and infect a bunch of people during the later stages of your infection. So you're going to get longer generation intervals. So this is, in all these scenarios, we all have same intrinsic generation interval distribution. So all these 3 individuals have intrinsically identical profiles of infectiousness, but the intervention measures are modulating how they're effectively transmitting in real life, and that's going to affect their realized generation interval distribution. And for example, putting this into simulation, we can show that. So now we have a simulation where reproduction number is something above 1, and then intervention kicks in, and then intervention is lifted. And then, for example, we have this infection curve that's driven by the changes in reproduction number, and the mean realized generation interval is going to look very weird and complex. But at this point, I hope you might be wondering, well, so what does that weird looking curve tell us about epidemic and the paper the renewal equation theory or a paper by Katie Gostick's paper, or I think the standard theory is going to tell us that, well, actually, we don't have to worry about any of these changes to calculate RT. We just need to know this magical intrinsic distribution for us to be able to estimate RT. And that's also what the theory tells us. So that's a little confusing because now, well, this is the generation interval we can measure in real life, but it doesn't tell us about, well, it doesn't tell us about, doesn't provide useful information. It doesn't seem to provide useful information about sort of estimating generation interval or estimating RT. So it tells us we can ignore this change. So that brings us to the next section, what I like to call instantaneous generation intervals. Now this part is, I think, a little abstract, and see how I can do it. So now going back to a little bit of math. So KT of tau is the average rate at which secondary infections are generated at time t by an individual who was infected at tau units ago. So this is sort of measuring the infectiousness of an individual. Effectively, how many new infections are going to transmit if they were infected tau units ago. And then if we integrate over this, we get RT. In particular, this RT is called instantaneous reproduction number in the literature, for which if we take the original definition that was first defined in 2007 by Christoph Fraser, I believe this is probably one of the first definitions, that it's the average number of people someone infected at time t would infect should conditions remain unchanged. And the key part is the last part, that should conditions remain unchanged. So this is actually a counterfactual measure of transmission if the conditions were to stay the same, which is rarely true in an ongoing epidemic because susceptible pools depleting, vaccines are introducing, interventions are changing, and the conditions are always changing. But this RT tells us this RT is a counterfactual distribution measure. And then likewise, if we normalize KT of tau by RT, we get this counterfactual generation interval distribution should conditions remain unchanged. So, and then we call this distribution the instantaneous generation interval distribution. And I'm not going to go into I got rid of the mathematics. I didn't put in the mathematics, but you can show that if the conditions actually remain unchanged, that this is a realized, this is going to be the realized generation interval distribution we see. And I'm going to say that the reason why the intrinsic generation interval is so vague is because it's a special case of this instantaneous counterfactual distribution. And to make this discussion a little bit more, hopefully a little bit more concrete, let's consider SIR model where people typically like to think about how beta is changing over time. So changes in beta is like changes in beta is the changes in transmission rate. So it's like for example, lockdowns or mask wearing, things like that would be attributed to change in beta. And actually, effectively, all existing framework, or the majority of, not all, it's not all, but majority, like 99% of existing framework mathematical framework focused on changes in beta t or changes in RT. But we can also imagine a case where gamma t is changing, and we can think about it in terms of faster removal of individual from I to R, essentially faster isolation. You're removing people from, you're not actually recovering them faster, but you're essentially making them, by going out and then identifying infected individuals and isolating quicker, you're effectively taking them out from the infected class. And then this is what the kernel looks like for this equation. Don't worry about the kernel. But now imagine a case. So A is showing a hypothetical change in beta. And then actually, one more thing. So now that there's something interesting, because now change in beta is only going to affect how transmissible you are. It's not going to affect your underlying time scale of infection, right? It's going if there's lockdown, you're going to transmit less, but your gamma is still staying the same. If you lift the lockdown, now you're transmitting more, but your gamma is staying the same. On the other hand, now if you're modulating gamma or if you're introducing isolation, you're directly affecting how people the time scale of transmission. That if you're isolating faster and faster, you're gonna see more and more earlier transmission because you're catching a lot of the late transmission. And so these two changes should have different impact. At least our intuition tells us that these two changes should have different impact on the generation intervals. So going to this example, moving on to this example, on figure A, we're showing a change in beta, and then this change in beta corresponds to this incidence curve shown in panel C. And it turns out that you can write down the identical change in gamma, panel B, which gives the same epidemic curve in panel C. So these are two different, A and B are two different epidemic scenarios, which are giving us the same incidence curve, same epidemic trajectory shown in panel C. And so let's focus, first starting with panel A, the change in transmission scenario. In this case is sort of what we discussed in earlier section, that the intrinsic generation interval stays the same, but the realized generation forward generation interval distribution changes. So initially, I should have labeled it, but anyway, so it's going down and up. So going down means your intrinsic real forward generation interval is decreasing over time, and then it's going to increase over time. And like I said, these changes absolutely don't matter in calculating RT. Oops, I should have changed the order of slides. So for example, here, the black line is the instantaneous RT that we want to calculate. And if we calculate it using mathematical theory, R Corey, the orange line is going to be, so R Corey and FPS. So R Corey is the continuous over time version of FPStim. I probably should have got rid of them. And then, so FPStim or the R Corey are giving the correct estimates of the instantaneous reproduction number, and then trying to incorporate these changes in forward generation interval distribution is going to give us some weird estimate that doesn't quite catch, which I think in the literature, some people have talked about trying to incorporate these changes in RT to generation interval to better estimate. Yeah, sorry, I'm reading the chat. The Bayesian epidemic is choice of smoothing window and some discretization that I wasn't quite careful about. So so the R core is continuous time version, epidemic some discrete time version. And so if we're only thinking about changing transmission, don't worry about changing forward how the generation intervals distribution is changing. It's going to give you biased estimates. But now if we imagine actually this second scenario where the isolations are half. So essentially increasing gamma, you can think of it as introduction of isolation. And then this is a partial lifting of the isolation strategy. And in this case, our instantaneous generation interval changes because you're modulating the individual level time scale of transmission directly through an intervention. And then that means that the black line is the true instantaneous reproduction number. But if we don't account for changes in generation interval distribution, orange line and blue line, our core and epidemic, we underestimate the reproduction number in this case. And interestingly, incorrectly using the R forward does allow us to capture some of the variation, even though it's incorrect. And the difficult part is if you want to correctly measure this, estimate this RT. Oh, sorry, did I go back one slide? I think I did. Yeah. If we want to correctly estimate this RT instantaneous reproduction number, we need to use this hypothetical instantaneous generation interval distributions. And so this is all in the theory world, and in practice, we basically can't tell the differences between the two because all we get is this time series trajectory, which doesn't tell us how the underlying intrinsic generation interval, this hypothetical generation interval distribution is changing over time. So conclusion or takeaway, well, I have more slides, but takeaway for this theory section is that realized generation interval distribution we can measure in real outbreaks from contact tracing are always changing, and these reflect changes in epidemic conditions. And if we're thinking about interventions that reduce transmission constantly throughout the course of infection, for example, social distancing or maskering, we don't have to worry about how these changes are happening, which is weird. Question. Actually, let me go through the takeaway and then I'll go to the question. And then, but if we have interventions that depend on time since infection, these changes in hypothetical distribution matter, but we can't measure them. So we can't measure them. So that's a problem from a data side. And I think that's a partly, so that's a problem. Yeah, I mean, I think it's kind of pointing at, well, so why do we care about so much about RT? I guess, well, yeah, I haven't quite articulated what so I'm not sure. It's a problem. I'm not sure what to say it, but two questions before I get to Sam. Caitlin Johnson is a question. So if you could have time varying GI into epidemic, would you be able to get back the true RT? Yes, you can, except that this time varying generation interval is a hypothetical distribution that you can't. So even if you knew when all infections were happening, you can't measure it. If you knew exactly when all infections were happening, and if you try to measure generation interval distribution, you can't get it because what you get is the forward generation interval distribution. In this case, it looks like some delay between instantaneous, but as you can see in this case, it's even if obvious there's a systematic differences between these things, and so we probably need some kind of statistical framework to try to get this counterfactual distribution back from forward. There's a lot more math in this unpublished manuscript, which I intentionally left out because I don't think I could explain. Sam has a question too.
Yeah, so where we can do stuff about this is if we're trying to estimate the effect of interventions and we have some underlying idea of how that intervention plays out, like whether or not it's going to affect transmissibility or if it's going to be like the contact tracing stuff or susceptibility to depletion you were talking about earlier. Could we put this structure into models of those kind and thinking stuff like Flaxman et al., that sort of thing, and then get better estimates of MPI interventions without being able to truly learn it from the data?
Yeah, I think it is possible to. So there is a way to write down, I guess. So like changes in RT, there's an analogous way to write changes in hazard. And so like, I guess if we're given incidence curve, we can try to assume, for example, what if all these changes were driven by gamma, then we can probably estimate this. If we assume what if all changes are driven by beta, we can estimate this. But it also tells us, I guess, well, if both assumptions giving us identical in epidemic trajectories, in some sense, why worry so much? I guess if our only pure interest is the ability to model and project, or actually, I'm not sure if the predictions, I'm not sure if the longer term predictions are going to, I think as long as susceptible depletion doesn't kick in, it's going to match up in there. I'm not sure how much longer, but I think since there are RTs different vaccination.
So I'm really getting it, not the out of sample prediction ability, but when you have an interest in saying like wearing masks does blah, which is what happens in like the Flaxman paper. And when they say wearing masks does blah, they're talking about its effect on
beta. So that in that case it does change. Yeah, if you're, and particularly again, if you had an isolation like change, But if you try to estimate it using like since you mentioned the Flexman like change, we're going to get quite different estimates because you're not capturing changes in generation interval. And have you thought about the implication of contact network where manipulating degree of distribution might modify? Yeah, so that's actually I didn't include it, but you can kind of generalize this framework in terms of changes in generation interval over space and contact network. I can kind of send the paper out when I'm done, but it's have you it's I guess yes, you can think about it, and then it's again when you think about contact network, you can think about local susceptible depletion and then how that affects real life generation intervals. But that is quite useful in that. Yeah, short answer is I've sort of thought about it, but I unfortunately didn't put it in the talk because it's kind of long, and happy to talk about it more.
Okay. Should we move on before we get bogged down in that very complicated topic?
Yeah, I was gonna move on. So dynamical biases and serial intervals. And so I've done some so far I've talked about theoretical aspects of generation interval distributions, and now try to talk about a little bit more practical things, but also again still talking about theoretical things because we need some theory to explain this. So the problem with generation interval is that we can't see them. We usually can't see when infections are happening. So people often focus on serial intervals, which is time between symptom onset, and to explain the difference between generation interval and serial interval distribution, we need some theory again. And so I took these slides from another talk, so it's going to be slightly disconnected from the previous thing. Anyway, so I think going back a little bit, going back, there's observed and latent processes in epidemic. So we observe confirmation of cases, but what we want to know is infection and onset. So these latent processes we can't directly observe, although I mean onset we can kind of observe. And then so one way to think about in order to go from infection to confirmation or confirmation infection, one way to think about is going forward. So we start from the time of infection and ask when do you develop symptoms, and that's going to give us incubation period distribution. So the key thing is that we're looking at people who are infected at the same time. We're looking at a group of people who experience primary event, in this case infection, at the same time, and then looking forward in time and asking when they develop symptoms gives us forward incubation period distribution. On the other hand, we can imagine going backward in time. We take everyone who develops symptoms at the same time. So let's say we get everybody who starts showing symptoms for COVID-19 today, and then asking when they got infected. And then the actual question to ask is this distribution going to be same as the other distribution if we look forward in time? It turns out it's not. So let's say we have an exponentially growing epidemic and then take everyone who develops symptoms on day 30 and then ask when they got infected. Then we're going to see a shorter backward distribution because epidemic is growing. The people who are showing symptoms, among the people who are showing symptoms, we're going to see those who are more recently infected, which in turn is going to give us a shorter observed distribution. And then turns out that this idea is key to understanding what serial intervals are. So again, serial interval is time between symptom onset and symptom onset. And then we can write down, so let's imagine there's some intrinsic serial interval, ignore the dynamics. Again, intrinsic is a very flimsy term, but I'm using it because I don't know why I'm using it, but I'm using it because for lack of a better word. But so let's think about sort of how intrinsically, without thinking of dynamics, what serial intervals might look like. So we can, so these 2 points, I don't know if can you see the cursor? Yeah, okay, Sam is nodding. So these are the symptom onset time. And then so from here to here, get here. So we have to subtract the incubation period of the infector. And then we add the generation interval. And then we add the incubation period of the infectee. And this kind of framework has allowed people to think that a lot of people concluded that, okay, the incubation period of the infector and the incubation period of the infectee is expected to have the same mean, so we can cancel them out. And then the mean intrinsic generation interval and the mean serial interval is going to have the same mean. And this is true if we're looking at actually grouping people based on infection time. So that's not a point, but so these, and then this, for example, this is what the resulting distribution would look like. So we have this intrinsic generation interval distribution, the intrinsic serial interval distribution, which has wider variance but same mean. And there's a problem with these distribution because so serial and generation interval are two distributions describing the equivalent process. So we expect them to give same biological answers about the process, but turns out using this serial interval is going to underestimate generation interval distribution, which has been, I think, prevalent in the literature, that using serial interval is going to give bias estimate of R naught or RT. But the problem is that this serial interval doesn't put dynamics into perspective. And implicitly, you're grouping people based on infection time. Instead, if you're starting from a reference cohort, so because serial interval is symptom to symptom, so we should be looking at people who develop symptoms at the same time. And then if we start from people who develop symptoms at the same time, then we go backward in time. We need we would subtract backward incubation period, and then add a forward incubation period, and then forward generation interval, and then add forward incubation period. And if the epidemic is growing, as I said, the backward incubation period is going to have a systematically different mean from the forward incubation period. It's going to be shorter. And when we take that into account, we now see that the forward serial interval distribution has longer mean than the forward generation interval distribution. And then this distribution allows us to recover the same reproduction number from the growth rate. And the mean forward serial interval is now also changing across different growth rates. I think I'm at 40 minutes, but I have a few more slides, which
you are, but I
I'll
think,
go
yeah,
over.
feel free to push through.
Yeah, I'll go through the other slides very quickly and then take questions. So how do we apply? So how do we apply this into looking at data? Particular, one of the questions that we were interested, or many people are interested in, does the Omicron variant have shorter incubation period and generation interval than Delta variant? This is in early 20, maybe not early, late 2020, early in the Omicron outbreak. Becker et al. Showed this data that the people infected with Omicron variant have shorter incubation periods, but the sampling collection is often backward. And then when we take into, I'm going to skip this slide of how I did the calculations. If we take, so during this period, Omicron is increasing and Delta is decreasing, meaning that you're going to see shorter incubation period for Omicron and longer incubation for Delta. When you take that into account, so A is the same, the observed distribution, and then B is the corrected distribution, in which case we get very similar looking incubation periods. So suggesting that the differences in the observed distributions might be partially can be driven by the differences in growth rates. And then using these, putting these differences into estimating generation interval from serial interval, we still find that generation interval of the Omicron is shorter than Delta. And this is because you have these interactions between, I'm not gonna explain, but and essentially demonstrating that you can incorporate these serial interval framework to better estimate generation interval distributions. And then when we take these new generation interval distributions and tries to estimate the advantage of Omicron variant. So previously from South Africa, it was estimated that there's fourfold advantage of reproduction advantage of Omicron variant. But if we take revised estimate, we get something like 2.6, which is far lower than the previous estimates. And I'm not saying that 2.6 is more realistic than 4. All I'm saying is that differences in generation interval estimates and using new generation interval estimates are going to hugely influence what you get out for estimates of these variant transmissibility and transmission advantages. Okay, so acknowledgements, questions. I skipped over a few slides and cut down the explanations for sake of questions. So feel free to ask if that was too fast. Sam has a question.
Could you summarize how the first part of your talk connects to the second part of your talk?
Not quite. So I cut down a lot of the second part of the talk. So second part so the theoretical framework presented in the first part is actually what allows us to calculate these serial intervals in the second part, and connecting in the sense that these changes in realized generation interval distributions are going to reflected in changes in realized serial interval distribution that we collect in real data is going to reflect. Oops, I'm going to go back a few slides. So these orange curves is changes in realized generation interval distributions, and these changes are going to be reflected in the contact tracing data we get. But the generation interval distribution that we need to calculate RT is this hypothetically unchanging intrinsic generation interval distribution. So even if we had perfect contact tracing data, it's going to be difficult to get. Well, so yeah, it's going to be difficult to get these kinds of hypothetical distributions. So one way to do it is by focusing on the initial epidemic growth rate. When things are staying constant, like you see the orange line overlaps with the black line. Well, so initially it works out very well. So you need these constant environment to be able to get these good estimates, but it's difficult. And we've done some work on it, but didn't put it in the slide because I wanted to talk more about theory than applications. And we have a question from Kelly. Samok had his hands up first, so I'll get to him first.
Yeah,
Questions?
Daniel, that was a really good talk, really interesting with the many intrinsics. And my question is about the first part. In first part, you said the case isolation can change the generation interval and it gives some bias in the estimate RT, right?
Yeah.
But I think in practice, it's a bit hard to find the exact time points to when the case isolation change in practice. But for example, we don't change the case isolation policy really as time goes by following the epidemic practice, right? But the generation interval change because of many things like risk awareness among general populations or risk awareness among the public health authorities or something like that. So in that sense, do you think that using the forward RT is better than the other RTs to consider the changes in risk awareness and gradual change in generation interval or something like that?
Well, I mean, so again, depends. I mean, depends on what factors driving. If it's like I said, I think some factors like people. So risk awareness is going to have two different effects, right? So risk awareness could just mean people are reducing contact, which could be beta T, but it could also have so we have a whole framework called strength and speed on this, which I find it. Well, I should say this. I'm an author. I find it's going to be abstract it's quite an abstraction, but so I didn't introduce. But anyway, but I like talking about beta and gamma because I think it's more tangible. So some changes driven by risk awareness is going to be changes in beta. You're going out less, you're wearing masks, and then so if those ones, you don't want to take into account changes in generation interval. But for example, if you're only wearing mask after symptom onset, then that's kind of like gamma. And if you're isolating faster after symptom onset because risk awareness, it's like changing gamma. So I think the point is that real world changes have both beta and gamma like qualities. And I guess this is sort of a frame, and then this is sort of a starting framework for trying to explain. I think the paper is supposed to be a little bit more sort of conceptual and pedagogical, that you can think about interventions into different. I guess this framework gives you like something more tangible. You can think about interventions into these two simple forms. And the short answer, I have no idea, but I think it's partly it's also trying to get at sort of the overemphasis on reproduction number. That the thing is, whether this beta changes in beta changing or gamma changing, your epidemic curve looks identical and your growth rate is going to be identical. But if you try to focus on the change in reproduction number alone, it doesn't. I mean, looking at this black curve and looking at this black curve, it looks like if we just show these two, we're gonna think, oh, they're very two different epidemics, but really they're same epidemics. So I guess let's put a little less emphasis on RT maybe. And although it is, I mean, it's anyway, going in circles. Kelly had a question first before going to Sam. What do you think is the most common misconception about epi-delay distributions? And I guess that's sort of not thinking about the dynamic bias into account. I think often you're looking at, say, people who. So if you look at literature, people will say we looked at people who develop symptoms between, say July 1st and July 14th, and then calculate incubation period of those people. And then if you do that kind of approach, you're looking at backward distributions, and that's going to be affected by your growth rates. And if you don't take that into account, you're going to get a systematically biased estimate of any kinds of delay. So this doesn't just apply to infection, it applies to any kinds of, say infection to mask wearing, infection to case identification, anything. And then so I think that's maybe maybe not the most common, but common mistake. I'm not sure what
it sounds like we need a best practices paper with good and bad examples.
Yeah.
I see a lot of bad papers. There's a lot of bad papers coming through peer review for sure. So, I mean, it would be good to have, a resource. If only someone was working on a paper like that.
Yeah, Sam and I are working on a paper like that, and I think several people here, actually, maybe just Kelly's not there here, but I'm the bottleneck. But Sam also had a question. He had his hands up for a while.
I did. Good question, and we really need to finish that paper. And I think I'm the bottleneck. But let's explain Kelly. It's Kelly's fault. But my question was, so we have this overemphasis on the reproduction number, which I totally agree with. In your expert opinion, what is the level of emphasis that we should have for it? Like, out of if it's like a mixture of these different things that we could focus on, how much should we focus on it and how much should we focus on other things? Just like ballpark, give me a number. 80% of our focus.
I think maybe like a 56%. I think it depends. So early in an outbreak, we don't really know. I think throughout there's an overemphasis on reproduction number, but it really depends on the type of interventions and the phase of an epidemic. During the initial growth phase, initial invasion, all we really see is the growth, and try to calculate or overemphasizing so all we see is growth rate, and whatever R you calculate is basically based on your assumption about generation interval. So unless you have a good reason to believe your generation interval distributions, I think forget about R naught. I mean, you can make reasonable assumptions that it's going to be similar to based on previous pathogen, or maybe you have some really early contact tracing data. In that case, great. But if you're trying to build some kind of deep mechanistic model with a bunch of compartments and making implicit assumption about generation intervals, it's probably not going to be the most useful thing. But if you're looking at something endemic, measles, vaccination are not obviously important. And also depends on the types of interventions. Again, if you're thinking about vaccination, we obviously need R naught. If you're thinking about social distancing, if R naught's 2, you want to reduce contact rate by 50%, you need R naught. But if you're thinking about isolation, essentially you can show that, again, the strength and speed framework, you can show that so how fast should the contact tracing be? The simple answer is, well, as fast as new infections are generating. So in that case, so if you can measure the speed of intervention, then you can show that as long as that is as fast as the speed of epidemic, you can get little r. So little r is just as a threshold as a big R. The growth rate is a threshold too. That little r equals 0 is a threshold as a big R equals 1. So and there's more work on that, which I didn't get to. But yeah, so different types of intervention matter and different phases of epidemic matters. So it's not quite 50-50, if it's kind of, it varies. If it's vaccination, but I mean also like depends on types of vaccination, right? You're trying to do ring vaccination and whatnot, then maybe there's both components. If you're try to do prophylactic in an ongoing outbreak, then if you try to identify cases and then vaccinate, sort of ring vaccination, then you want to identify people fast and then get vaccination as fast as possible and things like that. But anyway.
Yeah, that makes sense. We have time for one more question, I think, a quick one, if anyone has one. Okay, feels like not. That was really interesting, Daniel. Thank you. Are you happy to share your slides?
Very happy.
Okay, awesome. Could you post them on the community thread?
Yes, I will.
Okay, awesome. Yeah, so that just leaves us to do a very exciting clap thing for Daniel with our reaction buttons. How exciting. Show our appreciation. Whoa. Okay, I'm sure that's all the reward you needed, Daniel.
Thank you very much.
Awesome.
Thank you.